look at the final lecture for the unit on permutations and combinations, which is going to be an extension of the lesson from the previous time on Pascal's triangle, where we're going to more specifically identify what the binomial theorem is, and then use something referred to as the general term of the binomial theorem to identify or help identify specific terms within binomial expansion. So in the last lesson, we talked a little bit about a really simple binomial. So we have a binomial x plus y. It has two terms, raised to the power of n. Now, n is going to be a whole number. So it could be like 0, 1, 2, 3, 4, 5. And then we looked at the expansion for a bunch of different values of n. And the key thing we looked at is the coefficients on the different terms in the expanded binomials form something that's referred to as Pascal's triangle. And basically the way that Pascal's triangle works is you take, in a particular row, you can take any two of these coefficients, add them together, and it kind of gives you like this numerical value that's kind of like squeezed in between the two values below. Same right here, if you have the 1 and 2, and you look at the number below that's squeezed in between, that would be equal to 3. Same right here, 2 and 1 added together, and that would be equal to 3. We did also make reference to the fact that you can expand, write down Pascal's triangle in combination form, but in the previous lesson, we kind of just left the explanation for that to the side. So we'll very quickly explain like why you're allowed to write down these different coefficients in terms of combination form. And then afterwards, we'll just go ahead and solve various problems dealing with binomial expansion. So the example we use right here is we have the binomial x plus y, all to the power of 6. And again, that 6 right there just means you're going to take x plus y and you're going to have repeated multiplication of that binomial 6 times. So in this line right here, it shows you what that expanded binomial is equal to. Now, the point of this is by no means are we actually going to like manually multiply all these different binomials together, because it would just create a complete nightmare in terms of like the amount of mathematical operations you'd have to do and keeping track of all the different like terms. So we can use the different coefficients on Pascal's triangle to identify what the coefficients are for a binomial that's in a really simple form like this. Now, the one example we're going to use right here is we're going to try to explain why exactly is, so let's say we took x plus y to the power of 6, and let's look at forming the coefficient of the third term. So the coefficient of the third term is equal to 15, and we know that 6 choose 2 is equal to 15. Now, here's the way that you would think about why it is 6 choose 2. So first of all, like where does the 6 come from? Well, the 6 is the fact that you have 6 different binomials to pick from. So you have like a binomial here. So that's 1, 2, 3, 4, 5, and then 6. Now, what we're going to look at is how do you form specifically the y squared portion of this term? Okay, so y squared right here. Now, to get y squared, you would just need to multiply 2 of these binomials together, okay? X plus y plus times x plus y would give you a term that would have y squared in it. So the logic we would apply right here is we would say to get the y squared is formed by multiplying 2 of the 6 factors together. Now we look at this and we have, if we have 6 factors and we choose 2 of them to actually form the y squared, that's what leads to us getting 6 choose 2. So of the 6 factors, we choose 2 of them to form the y squared term. Now, the immediate question will pop up is, well, what about the x squared term? Sorry, not x squared term. What about the x to the power of 4 right here? Where does that come from? Well, if we use two of these factors to get the y squared term, to get the x to the power of 4 term, we would need to use the remaining 4 factors here. Okay, so what we have is x to the power of 4. So that's the x part of like term 3 in this binomial expansion. It is formed by multiplying okay, well, you no longer have 6 of the factors. We've used 2 of them to form the y squared term. So it'll be formed by multiplying 4 of the remaining 4 factors together. Now, if we multiply 4 of the 4 remaining factors together and write this in combination form, this would just be 4 choose 4. Now, to write down 15x to the power of 4, y squared, so in terms of where exactly that 15 comes from, so let's just write this down here. So we're going to have, maybe we'll do it up here. Okay, so we have 15 x to the power of 4 y squared. That 15 would be calculated by 6 choose 2. So that means of the 6 factors available, we choose 2 of them to form the y squared term. And then of the remaining 4 factors, we choose 4 of them to form the x to the power of 4 term. We have x to the 4 y squared. Now, this is a bit redundant. We don't really need to say like what we're choosing, that we're choosing the remaining factors to form the x squared term, just because 4 choose 4 is going to be equal to 1. So really what it comes down to is what exactly, how do we get the value 15? Like, yes, we can get it from Pascal's triangle. We can also think of it in terms of a combination form like this, which is basically you're just asking yourself, of all the factors available, how many of them do you have to use to actually get that y squared term? So let's fill in the rest of this binomial thinking of this logic right here. So looking at this first one, you have x to the power of 6. Now you'll notice immediately that I don't have any y term whatsoever, which basically means I'm not using any of the factors at all to form y. So what we'd write down is we would say 6 choose 0 x to the power of 6, because what that means is of the 6 factors available, we're not using any of them. And if I don't use any of them, you can't get a y term at all. Now for the second one right here, we have 6x to the power of 5 and y. So now I just have y to the power of 1. So the way we would get that coefficient is we'd say of the 6 factors available, we're going to choose one of them, because if you just pick one of them, it would be x plus y, which is to the power of 1. And that would give you y to the power of 1. So you'd have 6 choose 1, x to the power of 5, and then y. Okay, we already talked about how we get that third term right there. So the fourth term. Okay, so now we're using 3 of the factors to get y cubed. So that would then be, of the 6 factors available, we're going to choose 3 of them to get the y cubed term. And then that would be x to the power of 3, y to the power of 3, plus. Now we have the y to the power of 4 term, which means we need to use 4 of these binomials to get it. So we would say 6 choose 4. We're using 4 of them now. And then x squared. And then we would have y to the power of 4. And then plus for 6 here. Okay, now we have y to the power of 5. So of the 6 factors available, we're going to choose 5 of them to get y to the power of 5. So 6 choose 5. xy to the power of 5. And for the final one right here, we need to make use of all the factors to actually get y to the power of 6. So this would then be 6, choose 6, and then I would have y to the power of 6. Now, just notice a couple things with like the pattern in which we actually expand the binomial. So first things first, if we're in row number 6, notice that every single one of these choose expressions starts with a 6, okay? 6, 6, 6, 6, and then 6. Now, what then happens is we start off after the choose symbol with a 0. And as we make our way to the next term, we're going to start to see that value increase by 1. So this becomes 0, 1, 2, 3, 4, 5, 6. The other thing to note right here too is what is happening to the degree of both the x and the y. So I'll highlight that in purple. So here we start with x to the power of 6, and then every consecutive term, that power is going to decrease by 1. So go from 6 to 5 to 4 to 3 to 2. There's a 1 right there. And then it would be x to the power of 0, which is we don't see it at all. And then the final one is, well, what's happening to the exponent on the y? Well, in the first term, the exponent on the y would technically be y to the power of 0. Then it's going to start to increase in value by 1. Then it goes y to the power of 1, y to the power of 2, y to the power of 3, y to the power of 4, y to the power of 5, and then y to the power of 6. So this pattern is true if we have like a simple binomial like this right here, okay? Otherwise, we're going to have to make some adjustments in terms of if the first term in the binomial is not x and the second term is not y, like how we're going to have to account for that, but I'll come a bit later in the lesson. So let's go to the next page here. So what I just showed you on the previous page is what's referred to as the binomial theorem. So the binomial theorem, and again, this is the most generic binomial you can have, just x plus y all to the power of n. And again, we'll pick n values starting at 0. If it was 0, then the binomial will just be equal to 1. So that's simple. And again, just notice how it expands right here. So it follows the exact same pattern I identified on the last slide, which is for all of my individual terms, if you expand it, the number to the left of the choose symbol is going to match up exactly with the degree of the binomial there, or the degree attached to the outside of that binomial. So we have n, 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 etc. Okay. And then we're going to notice that onto the right side of the choose symbol, we start off with 0, then we increase in value by 1. So 0, 1, 2. Okay. And it says we eventually get to k and then all the way to n. So the last one you'd write down would be when the number on the left of the choose symbol and the number on the right of the choose symbol are identical. And then we look at the connection between the degree of the x and the degree of the y. So looking up right here, so the first term, we set x to the power of n. Then we start to decrease that value of n by 1. So n minus 1, n minus 2. And eventually we get to the point where the x term doesn't exist because it would be x to the power of 0. And the y just goes in the reverse direction. So here it would be y to the power of 0, then y to the power of 1, y to the power of 2, and it would go all the way up to y to the power of n. So even though it seems like it's complicated to express a binomial like this, it is significantly easier to expand a binomial like that as opposed to going back here and then, for example, foiling out these two binomials, then you have to start multiplying by each binomial individually. It would take you not an eternity to do it, but a lot of time to do it. And the odds of making a mistake are going to be really, really high. So the power of the binomial theorem is a way of expanding this without actually having to do all the individual polynomial multiplication operations. Now, we also have something referred to as the general term of the expansion of x plus y to the power of n. Now, what the general term does is it's a mathematical formula that tells you how to calculate a specific term within the binomial without needing to expand the whole thing. So for example, if I went back to like this question right here, and I just want to know what the value of term 5 is, we don't need to expand the whole thing to get it. We have a general term formula that can specifically tell me what that term is going to be equal to. Now, the way it is presented is it tells me, it says t k plus 1 is equal to n choose k, x to the power of n minus k, and then y to the power of k. I do want to point out that this is on the formula sheet. So if I just quickly show that formula sheet just down here. So it says in the expansion of the binomial x plus y to the power of n, that's the most simple binomial you can have, written in descending powers of x, the general term is t, that's a subscript, k plus 1, is n choose k, x to the n minus k, y to the power of k. Okay, now the tricky thing about this equation, or like really the only tricky thing about using it, is notice that it says t to the k plus 1. So for example, it says, yeah, it's not tk. So if you wanted to figure out what the value of the first term in the binomial is, you'd actually have to use a k value that's equal to 0, because then it'd be t to the t and then 0 plus 1. A k value of 1 would actually give you the second term, because then it would be k plus 1 plus 1 is 2. This will make a bit more sense if we actually go down to the example right here, though. Okay, so it says, determine the fifth term of x plus y to the power of 8. And again, we don't want to write down the full binomial expansion just because it's extremely time-consuming to do it. So in terms of what n is in the equation, n is going to be the exponent that's attached to the binomial. So we would have n is equal to 8. Now it says, what is the fifth term? Okay, so the fifth term would be t5, okay? But the way in which the binomial theorem is written is it's written as t and then subscript k plus 1. So what we have to do is, like, if it asks for the fifth term, I need to identify what does the value of k need to be to actually get the fifth term. So if we look at this, if we have 5 is equal to k plus 1, then the value of k would just be equal to 4. And we'll write that over on the side here. Well, now that you know what the value of n is and the value of k is, we can use this general term formula to figure out what the value of the fifth term is. So let's write it down. So it would be t subscript k plus 1 is equal to n choose k. And then we would have x to the power of n minus k, and then y to the power of k. Well, since we know what n and k is, we can just sub it into the equation now. So that would then be t to the 4 plus 1 would be equal to, and this would be 8 choose 4, and then x to the power of 8 minus 4, and then y to the power of 4. So we simplify this a bit. It would then be, okay, so it's now t of k plus 1. 4 plus 1 is 5. So this is term 5, okay? So we can confirm it if we just sub the k value back in. And then this would be equal to 8 choose 4, which would be, if we calculate 8 choose 4 would be 70. So we have 70. X to the power of 8 minus 4 would be 70. X to the power of 4. And then we just have y to the power of 4. So without doing the full binomial expansion, using the binomial theorem, we can use the general term formula to actually identify an exact term value within the expanded binomial. So term 5 has this value, and that's significantly less work compared to having to expand the whole thing. Okay, now this one says the middle term of a plus b to the power of 10. Okay, so first thing to identify is that exponent on the outside of the binomial. That is going to be the value of n. So we'll say n is equal to 10. Now, it's not very specific right here. It does say, like, what's the middle term, but it doesn't tell you what the middle term actually is. Now, one thing to be careful about is that when you actually expand a binomial, so a binomial to the power of 10 is not going to have 10 terms. It's going to have one more term than that, okay? Because if it was n to the power of 0, it would have one term. If it was n to the power of 1, then it would have 2 terms. So they're kind of offset by 1 right here. So we'll just say for n equals 1, or sorry, n equals 10, there are 11 terms. So now that we know there are 11 terms, well, then we can identify what the middle term is, because the middle number between 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is going to be 6. Okay. So the middle term is going to be term 6. Now be careful right here. Term 6 is equal to k plus 1, just the way in which the binomial theorem is written, which means that the value of k is going to be equal to 5. And again, we'll know this is right because when we sub it back in here, it's going to give us term 6 in the equation. So subbing it into the binomial theorem, let's plug it into the equation up here. I'm not going to rewrite it out. So what that would look like is you'd have t to the power of k, which not to the power of, t subscript 5 plus 1 is equal to n, which is 10. Choose k, which is 5. And then we'd have x to the power of n, which is 10, minus k, which is 5. And then we'd have y to the power of 5. So if we simplify that, so note right here now, we have t5 plus 1. So that's now going to give me term 6. And term 6 is the middle term. 10 choose 5. That has a value of 252. And then we would have x to the power of 5. And then we would have y to the power of 5. One thing to note, though, is that I didn't use the correct variable. So it's not x, it's a. And it's not y, it's b. We'll have to be a bit more cautious of this in just a moment when there's something a bit more complicated for those two parts of the binomial. So we'll just write down the term 6 then as being t6 is equal to 252, and then a to the power of 5, and then b to the power of 5. Okay. Example 2, it wants me to use the binomial theorem to write down the full expansion of x plus y to the power of 7. So yes, unfortunately, this is a bit tedious to deal with, but let's write it out. Okay, so we're going to say x plus y, okay, to the power of 7. Now we'll just note the pattern that I kind of showed on the previous page. So the first term is going to start off with 7. In fact, every one of them is going to have a 7 to the left of the choose symbol. Okay, we start off with 7, choose 0. And then we start off with the biggest value, the biggest exponent attached to x. So we'd have x to the power of 7. And again, what the 7 choose 0 means, it means of the 7 factors of this binomial, if expanded, we're choosing 0 of them to form the y term. And that's why I don't see the y term appearing at all. Okay, so let's continue the pattern. So we'll then go plus 7, choose. Now the number to the right of the choose symbol just starts to increase by 1. The x begins to decrease in value by 1, and the y starts to increase in value by 1. So right here, it was y to the power of 0. Now it's y to the power of 1. Okay, plus 7, and then we would have choose 2. So again, we're increasing that value to the right of the choose symbol by 1. X drops by 1. Y increases by 1. So 7 choose 2, x to the 5y squared. Keep it going. We then have 7 choose 3. And then x, we decrease it again. So now it's down to x to the power of 4. Y, we increase it to y to the power of 3. Plus, then 7 choose 4. And then we would have x to the power of, now it's down to 3. And y is up to y to the power of 4. And then we would keep going. We have 7 choose 5. And then that's going to be x to the power of 2. So the exponent on x drops by 1. The exponent on y is going to increase by 1. Okay, keep it going. We're going to keep going until the number on the left and the right of the choose symbol are identical. So we would have 7 choose 6. And then I would have x to the power of 1. And then y to the power of 6. And then we would have plus the final one is going to be 7 choose 7. Now the x is going to disappear because it's going to go to x to the power of 0. And the y is going to be the biggest exponent it can get, which is y to the power of 7. Well, we can calculate all these individual numbers. So 7 choose 0, that's just equal to 1. So the first term would just be x to the power of 7 plus 7 choose 1 is going to be equal to 7. So we'd have x to the power of 6 and then y plus 7 choose 2. That's going to be 21. So we're going to have 21. And then we would have x to the power of 5 and y squared. And then we have plus. Okay, so then it's going to be 7 choose 3. 7 choose 3 is 35, which is then going to be x to the power of 4, y cubed, plus 7 choose 4. Okay, that's equivalent to 7 choose 3. So it's going to be, again, there's equivalent combination statements. So it's also going to be 35. So it'd be 35, x to the power of 3, y to the power of 4. 7 choose 5 will have the same value of 7 choose 2. So that's back to 21 again. So we have 21, x squared, y to the power of 5, plus, and then we'd have 7 choose 6, which is equivalent to 7 choose 1. So that's back to 7 again. And we would have x, y to the power of 6. And the final one right here, which is 7 choose 7, would also be equivalent in value to 7 choose 0, which is 1. And then we'd have y to the power of 7. So we could use Pascal's triangle to identify what the different coefficients were, but we can also use the binomial theorem to also just do the fully expanded form if we want to use the combination notation. Let's just quickly check here. X to the 7, 6, 5, 4, 3, 2, 1, 0. Y goes from 0, 1, 2, 3, 4, 5, 6, 7. And that's my fully expanded form. Okay, now we're going to make this a bit tougher. So that general term formula that I showed you is only valid if the binomial looks like this, x plus y to the power of n. Now, if we look at this question right here, now the problem is I still have a binomial in brackets. It's 2x minus 5, but it's not x plus y. It's 2x minus 5. So what I'm going to do is I'm going to try to write it as close as I can into this format right here. So I'm going to try to write it as an addition statement. So I'm going to write this as being 2x, and we're going to say plus negative 5, and then all to the power of n. Now, the logic right here is we're going to do a substitution. So instead of it being x, it's going to be 2x. Okay? So instead of x, it's going to become 2x. And then here, instead of it being y, it's going to be negative 5. So y becomes negative 5. Now, what it wants us to do is to figure out what is the fourth term in the expansion of this. And again, just be aware the fourth term is going to be, you have to identify the k value as follows. So term 4 would be equal to term k plus 1, which means that the value of k needs to be equal to 3. And I can see it over on the side right there. Okay, the value of n, that's always going to be that exponent on the outside of the binomial. So that's equal to 6. So the way we approach this is we start off with the general term formula. Okay, we know what k is, we know what n is, but the difference right here is I have to do a substitution for what x is and what y is. So in this right here, we're not going to write down x. We're going to write down what x has been replaced with, and what x has been replaced with is 2x. Any replacement has to occur in brackets. And same right here, it's not y, it's negative 5. So anywhere where we have the y right here, we're going to replace it with what the actual value is. So it's negative 5. And again, substitute everything in its own set of brackets. So if we expand this, this would then be equal to, okay, 6 choose 3 would be equal to 20. And then in brackets, I would have 2x. Okay, let's subtract those exponents to the power of 3. We'll deal with that in a moment. And then negative 5 all to the power of 3. Well, negative 5 times negative 5 times negative 5. If you cube a negative number, it's still negative. So that would be negative 125. Now, the thing you have to be careful about right here is you have to use the power of a product rule, which means that you have to apply this exponent to here, and you also have to apply that exponent to the x. So if we properly expand it, then what it would look like is this would be 20, and then 2 cubed would be 8, and then x cubed is just, well, of course, x cubed. So we would have 20 times 8x cubed times negative 125, which then tells me that term 4 in the expansion of that binomial is going to be equal to negative 20,000 x to the power of 3. So if my binomial is not in the form x plus y to the power of n, I'm going to write it as an addition statement, and then I'm going to do a couple of substitutions. Okay, so let's go to the next page and do another one right here. So it says determine the fifth term of 3x minus 2y to the power of 7. So first things first, let's write it as an addition statement. So we're going to write down, this is going to be 3x and then plus negative 2y all to the power of 7. So in terms of what's happening right here, because again, the idea is we're trying to write it in this format, x plus y to the power of n. So it's not x here, it's actually 3x, okay? X is 3x. Okay, and we'll just color code that, I guess. So the 3x. And here, it's not y, it's negative 2y. So we'll write down y is going to get replaced with negative 2y. Again, the value of the exponent on the binomial, that is going to be the value of n. So we would have n is equal to 7. And the one thing you have to be careful about is if it does say it's the fifth term right here. So the fifth term is t5. But the way in which the general term formula is written as is it's tk plus 1. Okay? So if you equate these two, 5 is equal to k plus 1. This means that k has to be 4 to get t5. 4 plus 1 will be 5. So we'll just write down k is then equal to 4. Now, to get the fifth term, so let's write down the general formula. So I will write it here because I don't see it on this page. So again, that general term formula for the binomial theorem is t, k plus 1 is equal to n choose k. And then we have x to the power of n minus k, and then y to the power of k. So we're going to sub k and n in, but you also have to sub in what we're replacing x with and what we're replacing y with. So if I do that now, it would then be t, k is 4, so 4 plus 1. So note right there, 4 plus 1 will give me term 5, is equal to n, which is 7, choose, and then k is going to be 4. So 7 choose 4. Okay, now I do my substitution. So it's not x, it's in brackets 3x. And we're going to raise that to the power of n minus k, which is 7 subtract 4. And it's not y, it's negative 2y. So we're going to have negative 2y all to the power of 4. And now it's just a matter of correctly simplifying this. So if we do this, so first of all, it's not t4 plus 1, it's now term 5 would be equal to 7 choose 4 will be equal to 35. Okay, let's subtract the exponents here. So this would be 3x all to the power of 3. Okay, now this 4 here, it needs to go to two parts. So you can think of like this as being made up of negative 2 and also the y. So what the 4 has to do is the 4 has to be go to the negative 2 and it has to go to the y. So this would be negative 2 to the power of 4. So a negative number to an even exponent will be a positive number. So negative 2 to the power of 4 is going to be 16. Let's write that a bit more neatly. So 16. And then the y gets raised to the power of 4. Now, this 3 right here, same thing. Okay, so this 3 needs to go to both this coefficient 3 and it has to go to the variable. So what it would look like is you would then have this is equal to 35 multiplied by, okay, 3 cubed is 27, x cubed, and then 16 y to the power of 4. Okay, to combine, just multiply all the numerical coefficients together, and then we can just leave the variables as they are because they don't combine. And then I would get term 5 would be equal to, I'm just going to double check it right here. So 35 times 27 times 16, that's going to be 15,120. And then x cubed y to the power of 4. Okay, so that's term 5. And that's a pretty basic use of how the binomial theorem is going to operate. Now, we're going to look at problems that start to get a bit more complicated because they're not always going to be as simple as just figure out what term 5 or term 3 is. There's going to be other information that is unknown, and we're going to have to use a bit of logical reasoning to figure out what the unknown values are. Okay, so it tells us this. It says one term in the expansion of x squared plus a all to the power of 8 is 114,688 x to the power of 4. Now, what they want us to do is they want us to figure out what the numerical value of a is if a is a positive number. Okay, that statement where it says a is a positive number might become more relevant once we actually start to calculate it. Okay, so let's look at this right here and see what we're actually doing. So again, what you want to do is, again, you're trying to write down the binomial in this form, x plus y all to the power of n. So immediately I know what the value of n is. The value of n is equal to 8. Now, it's not x, it's x squared. So that's a substitution we're going to make. And it's not y, it's going to be a. Now, I don't know what term this actually is. It just says a term in the expansion of this is 114,688. So because I don't know what the term is, we're just going to leave k as being an unknown variable. We'll just say that k is just k. I'm not actually doing anything to it. Okay, now let's see how the work actually plays out. So this is the general formula of the binomial theorem. So tk plus 1 is n choose k, x to the n minus k, y to the power of k. So we can substitute the value of n in. So the value of n is 8. So we're going to plug it in here for 8. We're going to plug it in right here for 8. Now note the other substitutions that are occurring. It's not x, it's x squared. And it's not y, it's a. So if we expand that, then we're going to have tk plus 1 is 8 choose k, 8 to the power of. Now, in terms of where does 16 minus 2k come from? So now we have to use the product of a power of a power rule. So if you have a power and you raise it to a power, what you're going to do is you need to multiply these two things together. So we're just going to multiply by 8 minus k. And then that would just be equal to 16 minus 2k. So power of power, multiply the exponents together. Okay, so then we have tk plus 1, 8 choose k, 16 minus 2k, a to the power of k. Now, again, we don't know what exactly is the value of a, but we have to use a little bit of logical reasoning to actually solve this here. Okay, now if I look at the final term right here, okay, this final term does have x to the power of 4. So in this expression right here, we'll notice that the x term, it says x to the power of 16 minus 2k. Well, x to the power of 16 minus 2k, when simplified, has to be equal to x to the power of 4. So what I'm going to do right here is to figure out the value of k. Since x needs to be to the power of 4 because it tells me that's what the power is in that term, I'm going to take 16 minus 2k and I'm going to set it equal to 4. And that's going to allow me to determine what exactly the value of k is. So we're going to take this part of and again, this is as simplified as I can make the general term formula because I don't know what k is. So we have x to the power of 16 minus 2k. But we know that the term we're looking at has an exponent of x that's equal to 4. So this must be x to the power of 4. Now, if we have common bases on both sides, we can then set the exponents equal. So we then have 16 minus 2 times k is equal to 4. And then we just solve this linear equation. So to solve that linear equation, we can just subtract 16 from both sides. Subtract 16. And then I would have negative 2k is equal to negative 12. And then just to get k by itself, we can divide both sides of the equation by negative 2. Divide by negative 2, and then I would get a k value that is equal to 6. Okay, now I finally know what k is equal to. So what I'm now going to do is, because I know what k is, I'm going to sub it into this equation now and simplify this general term formula a bit simpler, okay? So let's pull this down here now, and now we're going to plug in k is equal to 6, and then this would then be t, and we'd have 6 plus 1 is equal to 8 choose 6, x to the power of 16 minus 2 times 6, and then a to the power of 6. Now, if we simplify this, this would then be term 7 is equal to 8 choose 6 is going to be 28. Okay, this up here, well, if I calculated k correctly, it should be x to the power of 4. And it is, because 2 times 6 is 12, and then 16 minus 12 is 4. So it would be 28, x to the power of 4, and then a to the power of 6. So that's a more simplified version of what the general term formula looks like. And now we know we're actually dealing with term 7. Now, what we then do is, well, we actually know what the value of term 7 is, because the question tells me the value of term 7 is 114,688. So what I'm going to do is I'll take this equation. I'm just going to take this value for term 7 and sub it in here. So if I do that, it would then look like 114,688 would be equal to 28. And then, oh, we forgot the x to the power of 4. Let's not forget that, because we're going to need that to cancel. So we're going to have x to the power of 4. And then this is equal to this expression we got for term 7, which is 28. And then x to the power of 4, a to the power of 6. Okay, we need to solve for a. Now, it does have a to the power of 6, but we'll worry about that in a moment. Let's just get a to the power of 6 isolated. So the way I'll do that is we're just going to divide both sides of the equation by 28. X to the power of 4 divided by 28. X to the power of 4. And now we'll notice, so this side, this goes away. This side, x to the power of 4 is going to cancel off. And then what I'd be left with, I'll write down the right-hand side of the equation first. We then have a to the power of 6 is equal to, and I believe that number is going to be 4,096. Now, I don't want to know what a to the power of 6 is. I want to know what a is. So to solve for a, what I need to do is I just need to get rid of that exponent, 6. And the way we do that is we can raise it to the power of 1/6, because then the power of a power rule will be 6 times 1/6, which is 1. Whatever I do to one side, I have to do the other side as well. So this would also be raised to the power of 1/6. Now, technically speaking, if you take like an even root, like a square root, a fourth root, a sixth root, your answer can be a positive or a negative number. So right here, we can actually get two solutions. You can get a is equal to +4 or -4. But this is why it clarifies this in the question. It says write down the value of a that's actually positive. So we'll say since a is positive, we would then have a would just be equal to +4. So that's a tougher question, okay? Because you don't know what the value of k is, and you have to use a bit of logical reasoning to figure out, I'd say mathematical reasoning to like figure out what the value of k is. After you know the value of k, you can set it equal to the term you know, and it's a matter of just figuring out that other piece of information. Well, let's step this up a little bit more now. Okay, so it says determine the numerical coefficient of the term containing a to the power of 7 in the expansion of 3 minus a to the power of 10. I do like how the book kind of organizes things. So where it says, like, what are we going to replace x with? What are we going to replace y with? What's the value of k? What's the value of n? Now, first things first again, okay, we want to write down the binomial in this form, x plus y all to the power of n. So I can take this and write it as an addition statement as 3 plus negative a, and then we're going to raise that all to the power of 10. So what this means here is it's not x, it's 3. And it's not y, it's negative a. The value of n is the exponent of the binomial, so that's going to be equal to 10. But once again, I don't know what k is, so that's a bit of a problem. Now, if you don't know what k is, what we're going to do is we're going to write down the general term formula, and we're going to try to simplify it as far as we can. Now, it does say, what's the numerical coefficient on the term that contains a to the power of 7? Well, let's worry about that in a moment. Let's write down the general term formula, sub these things in, and then we'll worry about the fact that we're looking for a term that has a to the power of 7 in it. So my binomial theorem again is t, k plus 1 is equal to n choose k. And we have x to the power of n minus k, y to the power of k. Again, I don't know what k is. There's not much I can do on the left-hand side right now. Okay, I can sub in 10. Choose k. Okay, it's not x here, it's 3. So I'll substitute that in brackets. So x is 3. Again, that's all to the power of n is 10. So we have 10 minus k. And it's not y, it's negative a. So we'll write down negative a and then all to the power of k. Okay, now, here's where you have to use this piece of information. So this is as far as I can go in terms of the general term formula. There's not really much I can do to actually simplify this thing. Now, whatever term we're calculating, it says it has to have a to the power of 7 in it. We can, by the way, expand this a little bit. Okay, so we have negative a to the power of k. Now, a different way I can write this is if I have negative a to the power of k, I can write this as being equivalent to negative 1 times a all to the power of k. So what I'm going to do is I'm just going to, the reason I'm doing that is because I want to separate the negative from the a. So we'll bring the k here, and we'll bring the k right there. So then I can write this as t, k plus 1 is equal to 10, choose k, and then we would have 3 to the power of 10 minus k, and then I can separate this one apart. So I can write down this one as being negative 1 to the power of k, and then we would have a to the power of k. I just separated it. Now, this immediately tells me what the value of what k needs to be, okay? So if I look at my actual general term formula, the only spot I have an a pop up is right here, okay? I have a to the power of k, and it tells me whatever term we're looking at, it also has a to the power of 7 in it. So what we would do is we would just say, okay, the one part of this equation right here that has a in it is a to the power of k. Now, we're trying to figure out a term that has a to the power of 7 in it. So immediately that tells you that the value of k has to be equal to 7. Okay, so we can go back here now, and now this is equal to 7. So this now enables me to simplify this equation because now I know what everything is. I know what k is. So we can then write down t, 7 plus 1, is equal to 10, choose 7, and then 3 to the power of 10 minus 7, negative 1 to the power of 7, and then we have a all to the power of 7. Okay, so note right here, by plugging in k equals 7, well, then I'm going to have a term that has a to the power of 7 in it. Okay, let's simplify. So this is actually term 8 if k is 7. 10 choose 7 as a value of 120. Okay, this will simplify. So we'll turn it into 3 to the power of 3. Negative 1 to the power of 7 is going to be a negative number, so negative 1. And then a to the power of 7, I'm not going to do anything with it. Okay, it's just going to be the variable part of this term. So then this would be equal to 120 multiplied by 3 cubed is going to be 27 times negative 1, and then times a to the power of 7. And if we simplify just by multiplying all the coefficients together, I would then get term 8 is equal to, and this would be negative 3, 2, 4, 0, a to the power of 7. And what the question says right here is, what's the numerical coefficient on the term that contains a to the power of 7? Well, the numerical coefficient is just this. So we'll just say the numerical coefficient would be equal to negative 3, 2, 4, and then 0. So again, it's another one of these questions where I don't know what k is, but since it tells me that my term has to have a to the power of 7, I can use mathematical reasoning to figure out what k is. All right, let's do one more. This is going to be as hard as it gets. For example, number 7 here. Now, it says determine the constant term. So the constant term is not going to have a variable in it in the expansion of 2x minus 1 over x squared all to the power of 15. Now, the thing you have to be careful about right here is that some people might say to me, okay, well, n is equal to 15. Yeah, that's totally true. Okay, n is equal to 15. And if n is equal to 15, then that means that if n is equal to 15, then it means that this binomial has 16 terms. Okay, and then what people usually assume is that the constant term is always the last term. That's not always true. Okay, so right here, we don't know what this is going to look like if we actually expand it. And what we do not want to do is do not assume the last term is the constant term. So we can't just say that term 16 is going to be the constant term. Okay, we don't know it. Okay, especially because we have like an x here in the numerator and an x squared in the denominator. So I'll make a quick point right here. Do not assume the constant term is the last term. Okay, so be very careful about this. Now, what do we know about the constant term? Well, the constant term is not going to have an x. So if the constant term is not going to have an x, what does the exponent on the x need to be? Well, if the x isn't going to be there at all, it needs to be an exponent of 0. So the term that has x to the power of 0, okay, that's going to be the constant term. Now, I still don't know what that is because it doesn't tell me which term it is. This is another one of these questions where I don't know what k is. So we'll say k is equal to a question mark. Now, furthermore, this is a really ugly expression. So again, we want to try to write things in the format x plus y all to the power of n. Okay, so I'm going to do that. So I'm going to write this down as being 2x plus, okay, and what I can write down is negative 1 over x squared all to the power of 15. Now, I still don't like that because now I have a denominator and I don't want that at all. So all I'm going to do is I'm going to rewrite this so the x is in the numerator. And if you do that, we would then have 2x plus, in brackets, negative x If you have x squared in the denominator and you move it up to the numerator, we can just write it as a negative exponent. So we'd write down negative x to the power of negative 2, close a bracket off, it's equal to 15. So here, it's not x, it's 2x. So let's clarify that substitution. Not x, it's 2x. And then here, it's not y, it's negative x to the power of negative 2. So it's kind of a nasty second term that you have in the binomial. And it will make it a little bit of a pain to properly simplify, but we'll deal with that in just a moment here. Okay, so y is becoming negative x all to the power of negative 2. So again, what we're going to do is we're going to start off by writing down the general term of the binomial theorem. We're going to expand it as far as we can. And then we're going to make use of the fact that we know the constant term has to have an exponent of 0 on the x, because that's the only way you're getting rid of the x. So general term formula is t, k plus 1, is equal to n choose k, x to the power of n minus k, and then y to the power of k. All right, so let's sub in what we know. Okay, I can't sub in k. I don't know what it is yet. We will know it shortly though. Okay, n is 15, so we would have 15, choose k, and then we would have x to the, oh, it's not x though. It's 2x. Let's make that substitution. So yeah, it's not x, it's 2x. So we'll have 2x all to the power of 15 minus k. And then we have, it's not y, it's negative x to the power of negative 2. So we're going to have negative x all to the power of negative 2, and we're going to raise that to the power of k. All right, this is kind of unpleasant to simplify. So the problem right here is I have two different parts of the general term formula that have x's in it. And what I want to do is I want to try to find a way to combine the x's together so I only see a single x with like some kind of combined exponent. Okay, so let's try to break down how to do this right here. So let's write down t, k plus 1 is equal to, this would be 15, choose k. Now, what I can do here is this is the power of a product. So I can apply this exponent to the 2, and I can also apply to the x separately. Again, I'm doing this because I want to find a way to get x combined with the 1 over here. So I need to separate the 2 from it. So what it would then look like is it would be 2 to the power of 15 minus k, and then it would be x to the power of 15 minus k. Now, as for this right here, okay, we've got that negative. So I'm going to apply a similar trick to like what I did up here to kind of like deal with that negative. So if I have, maybe I'll just show it over on the side right here. So if you have negative x to the negative 2 to the power of k, an equivalent way of writing this is square brackets, negative 1, and then x to the negative 2, and then all to the power of k. So the reason I did that is I'm trying to separate that negative from the x, just like right here, I was trying to separate the 2 from the x. Well, now that you've done that, you can then use the power of a product rule. So I'll apply the k to the negative 1, and I'll apply the k to that negative 2. So what this would then expand to is it would become negative 1, and then it would be to the power of k, and then it would be x to the power of, okay, now this is power of a power rule. So power of a power rule means multiply the exponents together. So that would just be negative 2 times k, which is negative 2 times k. Now, it looks like a really ugly expression, and it is. Now, what I want to do, though, is I want to combine the two different x parts together, okay? Now, I can do that. So if you have two common bases, which I do, okay, so the bases are x and x. That's why I separated the negative 1 from this guy. and I separated the 2 from this one right here. Okay. Now, once I have common bases, if you multiply common bases together, what you do is you add the exponents. So what I'm going to do is the exponent 15 minus k and negative 2k, we're going to add those two expressions together. So let's write it out now. This would then be t k plus 1 is equal to, and it would be 15, choose k, and then 2 to the power of 15 minus k. We'll do the x's at the end right here. Let's write down that negative 1 all to the power of k. Okay, now let's combine these exponents together. If you add them together, negative 15 minus k minus 2k, the negative k and the negative 2k are like terms. So that will combine to give you 15 minus 3k. Okay, now we have to use our reasoning right here. So the whole idea is if this is the constant term, this x value cannot be here. Okay, x can't be here at all. So what I need to do now is for constant term, I'm going to take the x in my simplified expression for the general term, which is x to the power of 15 minus 3k. And what I need is I need x to the power of 15 minus 3k to be equal to x to the power of 0. So I'm going to try to find a value of k that's going to make the exponent on this 0, because if I do that, then the x is going to disappear. And then I have my constant term. My constant term, as it says up here, is independent of x. So we set it equal to x to the power of 0. Okay, well, let's solve for x now. So we then have 15 minus 3k is equal to 0. So we're going to subtract 15, then we'd have negative 3k is equal to negative 15. And then I'm going to divide 3k, or divide by 3, divide by negative 3. And then, I mean, you could have seen this easily even before. You probably didn't need to do the mathematical algebraic work on this, but we're going to get a k value that is equal to 5. Okay, once you figure out what k is, these problems get significantly easier. So now we go back up to the top right here and we just identify, okay, k is actually equal to 5. Now, what I'm now going to do is, well, it says, what is the value of the constant term? Well, if I plug in the value of k here, everything will simplify to a single numerical value, okay? So let's see how this works. We're going to take k, and that's 5. We're going to plug it in here. We're going to plug it in here, 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 and then here, and we'll see what we get. So this would then be t, 5 plus 1, is equal to 15, choose 5. And then we're going to have 2 to the power of 15 minus 5. We have the negative 1 right there, also to the power of 5. And then we have x to the power of 15 minus 3 times 5. So notice right here, 15 minus 3 times 5 is going to be 0. X to the power of 0 is going to get rid of that variable. Now, note right here, this is term 6. So just kind of re-emphasizing this point up here. So I said, do not assume the constant term is always the last term. So the constant term in this expansion is actually not the last term. It's term 6, okay? It is not term 16. So 15 choose 5 is equal to, I believe it's 3003. So we have 3003. Okay, then we have 2 to the power of 10. Negative 1 to an odd exponent is going to be a negative number. And then this is going to be 15 minus 15, which is x to the power of 0. So then term 6 would be 3003 multiplied by 2 to the power of 10 is 1024. Don't forget that negative at the end, so negative 1. And then x to the power of 0 is just 1, so it's gone. Okay, and that's the key thing with this question. We need to identify that if it is the constant term, then the power on the x has to be equal to 0, and that's how we figured out what the value of k is. So the constant term, which is term 6, would then have a value of negative, and I believe it is negative 3 million. $75,000 and 72. Let's double check that, okay? So it is negative 3075072. And like I said, that's probably as difficult as a problem is going to get with like using the general term formula from the binomial theorem, trying to figure out what the constant term is. All right, that's the end of this lesson. So the questions you can complete to reinforce this material are numbers 1, 2, 3, C, D, and E, 4B, 5B, 6A, 7B, 8 through 13. Check that quickly again. And that is the end of the unit on permutations and combinations.